Section 1 Introduction. We're going to delve into the world of large language models, LLMs, which have shown remarkable abilities in understanding and generating text. However, they're not perfect and can sometimes produce undesirable results, such as toxic language or irrelevant information. We're particularly interested in how these models can be fine-tuned to better follow instructions and produce more accurate results. Imagine you're giving a model a prompt to generate text. Sometimes, the model might produce text that, while fluent and relevant, doesn't quite follow the instructions you gave. This is a problem we're trying to solve. Traditional methods used to guide text generation, like nucleus sampling or beam search, don't always consider future costs, which can lead to these deviations. To address this, we're proposing a new approach that considers future language constraints when generating text. We're introducing a future constrained satisfaction score, which essentially measures how closely the generated text aligns with the given instructions. This score guides the model in generating the next piece of text, helping it stay on track. However, estimating this score can be quite complex. To overcome this, we're building on previous research that uses large language models to evaluate candidate outputs based on their generation probabilities. We're proposing a method to estimate future constraint satisfaction, which will help us find the best sequence in the infinite output space. To make this process more efficient, we've developed a beam-based algorithm that generates sequences from left to right. Our experiments have shown improvements in 3 areas: generating text with specific keywords, reducing toxicity, and improving factual correctness in question answering. Now, let's get a bit technical. When a language model generates text, it does so step by step, from left to right. It uses the given prompt and the text it has already generated to predict the next piece of text. In our work, we're tweaking this process to ensure the generated text exhibits specific desired behaviors, like reduced toxicity or the inclusion of certain keywords. We're doing this by modifying the conditional sequence probability, which is the probability of generating a particular sequence given the prompt. We're introducing a future constraint satisfaction score into this probability, which measures how well the generated text aligns with the given instructions. For example, if we want to generate a sentence with the keywords, "run team field drill," we can set these keywords as the constraint. The model will then generate text that includes these keywords, guided by the future constraint satisfaction score. This score can be estimated using any pre-trained language model, and it can be broken down into several sub-scores, each measuring a different aspect of the constraint. By combining these sub-scores, we can get a better idea of how well the generated text meets the set constraints. Section Summary. Large language models, LLMs, have impressive text understanding capabilities, but they often exhibit undesirable behaviors like toxicity and deviation from provided prompts. To address this, we propose a novel approach that incorporates a future constrained satisfaction score to guide text generation. By estimating this score, we can choose the best next token to ensure the model follows the specified instructions. Experimental results show improvements in tasks like keyword-constrained generation, toxicity reduction, and factual correctness in question answering, highlighting the potential of our approach for faithful decoding with LLMs. Section 2.1 Estimation of future constraint satisfaction. In our approach, we use future constraint satisfaction to guide text generation while maintaining the decoding efficiency of large language models. This section explains how we estimate future constraint satisfaction with these models. We calculate the future constraint satisfaction score of C, X, by using the log likelihood of generating the constraint based on the prefix y, t. This is represented by the equation r, y, t, c, x, equals log p, c, x, y, t, sep, c, x, where sep is a special token that separates the two sequences. Some recent studies have also suggested estimating such scores or rewards in a binary question answering format. So, r, y, t, c, x, equals log, p, yes, prompt, p, yes, prompt, plus p, no, prompt, where p, yes, prompt, and p, no, prompt, are the probabilities of generating yes and no as the next token, based on the prompt, respectively. In this section, we demonstrate how our proposed method can be applied to specific natural language processing problems. It's important to note that we rely solely on the likelihood of pre-trained language models to estimate satisfaction in this study. While this provides significant versatility and flexibility, it may not always produce accurate estimations. One could use fine-tuning and parameter-efficient techniques like LoRa to better tailor the estimation process, providing more accurate and flexible evaluations of constraint satisfaction. We plan to explore this in future work. Existing decoding methods like beam search or nucleus sampling decide which token to generate in a left-to-right manner. Due to their inherent constraints, these methods may produce less than optimal results. This can be improved by proactively considering future costs. Specifically, we consider the following decoding objective: y equals argmax, y in y, log p, y, x, plus lambda asterisk r, y, c, x, where y is the set of all sequences and lambda is a weight coefficient. P, y, x, represents the conditional probability distribution by a language model, and r, y, c, x, is the estimated satisfaction score for constraint c, x. This optimization problem is computationally challenging, so we use the beam-based search algorithm to solve it approximately. Given the current prefix y, t, a new token y, t, is predicted at each step, and we select the top k best candidate tokens using the following criterion: y, t, equals arg, top k, y, t, in v, t, log p, y, t, x, plus lambda asterisk r, y, t, c, x, where v, t, is the candidate output space at position t. We define v, t, as the top two asterisk k candidates in cumulative probability mass p, y, t, x. Additional tokens may be added to this candidate set. For example, in keyword-constrained generation tasks, we introduce another token set, v, keys, which consists of tokens found in keywords. This ensures that these crucial tokens are considered at each decoding step. We repeat this process until certain conditions are met, such as encountering an end-of-sequence token or reaching the maximum allowed length, etc. In the end, we choose the candidate that achieves the highest score according to the equation from the top k candidates. We test the performance of our proposed method on 3 different tasks: keyword-constrained generation, toxicity reduction, and factual correctness in question answering. In our first task, we focus on lexical-constrained text generation using the Common Gen dataset. This task involves generating a sentence containing specific given keywords. For example, given a set of concepts, e.g., car, drive, snow, the goal is to generate a fluent sentence that incorporates these concepts, e.g., I drive my car during the winter through the snow. We evaluate the generated outputs using automatic metrics of fluency, blue, cider, etc., and a constraint coverage score. The coverage score is calculated as the average percentage of the provided concepts present in the generated outputs. Section Summary. In this section, the authors propose a method that utilizes future constraint satisfaction to guide text generation in large language models. They estimate the future constraint satisfaction score using the log likelihood of generating the constraint conditioned on the prefix. They also discuss the limitations of relying solely on likelihood and suggest leveraging fine-tuning and parameter-efficient techniques for more accurate estimations. Additionally, the authors introduce an inference method that proactively accounts for future costs and use a beam-based search algorithm to solve the optimization problem approximately. They demonstrate the effectiveness of their method on tasks such as keyword-constrained generation, toxicity reduction, and factual correctness in question answering. Section: Lexical Constraint Satisfaction Evaluation. We're going to discuss how we evaluated the ability of language learning models, LLMs, to predict future constraint satisfaction. To do this, we set up a ranking benchmark. In this benchmark, each sample is made up of a pair of sentences. The first sentence, which we'll call A, has a constraint, while the second sentence, B, does not. Sentence A is taken from the Common Gen development set, while sentence B is a complete sentence generated by ChatGPT using a few starting words from sentence A. Our theory is that if sentence B doesn't include all the specified concepts, it should be seen as a negative sample compared to sentence A. We also looked at a different situation involving a pair of sequences, which we'll call hat A and hat B. These sequences are similar in length and are incomplete. The only difference between them is the last word, while they share the same prefix. Specifically, hat A is the prefix of sentence A, and hat B has the same prefix as HATA, except for the last word. The last word in HAT B is a randomly chosen word from sentence B. Even though HATA and HAT B only differ by one word, it's important to note that their tokenized sequences may have different lengths. However, the difference in length is small. For each pair of sentences, A and B, we assign a ranking accuracy score of 1 if the ranking of A with the constraint is greater than the ranking of B with the constraint. If not, the ranking accuracy score is 0. Our results showed high accuracies over sentence pairs. However, accuracy significantly drops for prefix pairs, suggesting that estimating satisfaction for prefix pairs is considerably more challenging. We also noticed that models based on natural language inference, NLI, performed well, despite their significantly smaller model sizes. Next, we looked at the effect of the lambda parameter in our proposed method. We found that when lambda is in the range of 1 to 10, our method consistently achieves higher coverage scores, indicating a higher percentage of provided concepts present in the generated outputs. However, setting a very large lambda can excessively weigh on the constraint satisfaction term and hurt performance. With the selected lambda parameter on the development set, we observed high-quality outputs from these instruction-tuned models. Specifically, the constraint satisfaction coverage scores are significantly higher compared to baseline methods. Next, we considered another task, reducing toxicity. Given a prompt, the task is to generate a fluent continuation but not with a toxicity attribute. We characterized generation toxicity using the toxicity score from Perspective API. We also evaluated our generations for fluency and diversity. In our proposed method, we reweight the top 50 token logits from LLMs with our future constraint satisfaction score, then truncate the logits that are in the top K, top P vocabulary at each position, effectively assigning 0 probability to tokens outside the vocabulary. To evaluate the quality of toxicity constraint scores from LLMs, we established our ranking benchmark. We created sequence pairs where one sequence is less toxic than the other. We assigned a ranking accuracy score of 1 if the ranking of the less toxic sequence with the constraint is greater than the ranking of the more toxic sequence with the constraint. If not, the score is 0. Many open LLMs demonstrated an accuracy surpassing 50%, which represents the performance of random guessing. Particularly, the model Falcon 7B Instruct exhibited superior performance. However, a few models achieved an accuracy exceeding 60%, indicating potential for improvement in the future. Section Summary. To evaluate the quality of future constraint satisfaction using language models, LLMs, a ranking benchmark is created with sentence pairs. The benchmark shows that satisfaction estimation for prefix pairs is more challenging, but many LLMs still achieve over 60% accuracy. In terms of toxicity reduction, LLMs are evaluated using a toxicity ranking benchmark, where many models demonstrate accuracy surpassing 50%, with Falcon 7B Instruct performing exceptionally well. Section. Results. We've been studying the reduction of harmful content in 2 different large language models, LLMs, Falcon 7B Instruct and Alpaca 7B Instruct. We've noticed a slight decrease in the variety of their outputs, but we've also found that they're less likely to produce toxic content. We didn't include Llama 2 to 13B chat in our study because it already has a low toxicity level. Our tests showed that the average highest toxicity score is around 0.135, and the average likelihood of toxicity is about 0.01. One of the challenges with these large language models is that they sometimes generate information that isn't based on reality, a phenomenon we call hallucination. Despite their ability to produce smooth and coherent text, it's crucial that they provide accurate answers backed by solid evidence. To address this, we're working on reducing hallucination. We used the ALSE dataset to test the model's ability to answer factual questions. This dataset provides a set of passages for each question, and it also provides a way to evaluate the correctness of the answers. For short answers, we check if the model's response contains the correct answer from the dataset. For longer answers, we measure how many of the model's responses include the 3 provided sub-claims. We used 2 shots for each question and 3 documents. We also compared our method with 2 other methods that use a deterministic search, greedy decoding and beam search with a beam size of 5. While nucleus sampling is often used for generating open-ended text, we didn't see a significant improvement in performance compared to greedy decoding in our initial tests. We created a benchmark for factual correctness using the fact verification part of the true dataset. We focused on the fever and vitamin C sections of the true dataset. For each piece of evidence, we chose one claim that was supported by the evidence and one that wasn't. If the model gave a higher score to the supported claim, we gave it an accuracy score of 1. If it gave a higher score to the unsupported claim, we gave it a score of 0. We found that several LLMs achieved an accuracy of over 60%. Interestingly, we noticed that the performance of the Llama 1 family model on the fever ranking part decreased as the model size increased. We also looked at samples where the documents supported the answers. This approach helped us reduce the impact of noise in the data and get a more accurate measure of correctness. In general, we found that beam search performed about as well as greedy decoding in terms of factual correctness. However, our method showed a significant improvement in factual correctness compared to the other two methods. We also tested our method using the retrieved documents and subclaims as constraints. Our method showed improvements in both cases, especially for the Vicuña 13B v1.3 model. When we tested our method on the full Explain Like I'm 5 dataset, we found that the lack of high-quality supporting documents led to a significant drop in the average performance of all models. This highlights the importance of having accurate and reliable supporting documents for question answering tasks. In terms of speed, our method is slower than greedy decoding and standard beam search because it has to compute 2*k candidates in the equation. However, this increase in decoding time is a reasonable trade-off for more accurate generation. There are several ways to reduce the time and maintain the quality of the generation, such as choosing a smaller K or using smaller, tuned LLMs that can compute the future constraint satisfaction score. Section Summary. The toxicity reduction on two different LLMs, Falcon 7B Instruct and Alpaca 7B Instruct, resulted in a minor decrease in diversity. Factual question answering is crucial in mitigating hallucination in large language models, and the ALSE dataset provides a benchmark for evaluating correctness through short answers and subclaims. Our proposed method demonstrates significant enhancements in factual correctness compared to baselines, and the absence of high-quality supporting documents leads to a decrease in overall performance in question answering tasks. Section: Human Evaluation. We carried out a human evaluation to assess the impact of various decoding methods. This was done using the complex long-form question answering task known as ELI5, which typically requires lengthy responses and multiple evidence passages. We randomly selected 30 questions and asked Amazon Mechanical Turk workers to evaluate the model's responses based on 3 criteria, inspired by previous human evaluation studies. Firstly, we looked at fluency, scoring from 1 to 5, to determine if the generated response was smooth and coherent. Secondly, we assessed informativeness, again on a scale of 1 to 5, to see if the response effectively answered the question. Lastly, we evaluated correctness, scoring from 0 to 3, to check if the claims made were fully supported by the response. This score was later normalized to a ratio of correctness. Our proposed decoding method proved to be quite effective, as it received higher scores in all categories, particularly in correctness. In the past, there have been several works like Control, PPLM, Getty, and Fudge that focused on controllable generation. These methods typically use additional code or attributes to control the generation. They also use a tuned classifier or auxiliary model to modify the output distribution. The control in these methods is limited to a label or a category of the sequence. In contrast, our work verbalizes constraints in natural language, meaning any natural language constraint can be applied to our method. We use the knowledge or understanding of powerful language models to guide the constrained text generation. Another related approach in constrained generation involves refining the text with language models after each completion. This model iteratively edits the generated text, often requiring multiple generations, especially for long-form question answering tasks like Explain Like I'm 5. Another aspect of constrained decoding is related to reinforcement learning. In this approach, the generator model parameters need to be updated. Additional training is conducted involving both the generator and a reward model. Our work is inspired by a search algorithm that seeks the highest scoring path by using heuristic estimations of future scores toward the goal. Recently, several heuristics have been developed to estimate look-ahead scores. Unlike our work, they estimate lexical constraint scores using fixed-size look-ahead steps in lexical constrained tasks. In the work of Fudge, an auxiliary binary classifier is trained with random input sequence truncation. Recently, a token-level discriminator was learned for knowledge-grounded dialogue and abstractive summarization. In our work, we estimate a future constraint satisfaction score with verbalized constraints and language models.